Hello and welcome to the session. In today's session, we will do analysis of three very simple algorithms. One is relating to squaring or cubing a particular value. The other algorithm relates to matrix multiplication. And the third algorithm is about exponentiation. But what should be the basis of doing analysis of these algorithms? There has to be a complexity calculation. So what we have selected for presentation of these algorithm or for analyzing these algorithm is the big O notation, right? So I am defining the big O notation in this particular slide, where to represent the what big O notation does, it represents the upper bound or worst case of an algorithm, which finds the maximum number of steps to be to solve a particular problem. So basically, big O is going to give you maximum number of steps, right, for solving a particular problem. And if we can define the maximum number of problems, then we will be able to know the worst case behavior of that particular problem. But what are the advantages of using big O notation? After all, why we are just interested in worst case? Well, why we are using upper bound is it bounds the growth of the running time from above for large values of input sizes. So topmost values are bounded, right? It notifies that a particular procedure will never go beyond a specific time for every input size n. So you are able to define the maximum time needed by a particular problem. And advantage is basically it makes algorithms much easier to analyze, since we are conveniently we can conveniently ignore low order terms. So we will be just interested in the highest order term of the polynomial, and that is what is going to give us the complexity of that particular algorithm. But how we are defining this particular big O notation? Well, this is once again we are giving over here. Let fn and gn be two positive functions, which are also shown in graph. Fn is represented by this particular line, whereas gn is being represented by this particular cgn. It's not just gn, gn multiplied by some constant. So c can be any constant. Okay, be two positive functions, such functions each from the set of natural number domains to positive real number range, right? So basically n is basically containing the value of natural numbers, and the real numbers is the range, that is the gn value or the fn value. Then how we are defining big O notation? Fn equals to big O g of n if there exists two positive constant. We need two positive constants c and n0 such that fn is always less than equals to cgn for all n greater than equals to n0. So look into the graph and it will be becoming very clear to you that below n0, right, you may find that fn is more than cgn, but beyond this particular n0, right, so beyond this particular value n0, this particular cgn is more than fn. So this basically is showing us an upper bound for the value above n0, not below n0, right? So it makes the order n, the big O of gn for the value n is greater than equals to n0. So for this is the way we define the big O notation of ours. So once we have defined the big O notation, let us try to look into some of the simplest algorithms and how we can represent these algorithms into big O notation or their complexity in big O notation. The very first algorithm which we are going to discuss is summation algorithm for computing I cube. Right. So basically this is from I is equal to 1 to n. We are just computing I cube. What does it mean? 1 cube plus 2 cube plus 3 cubes till n cube. So this is the way we are going to compute the cube of them. Now, the algorithm is very simple. In fact, we have not represented algorithm, but it is almost an implementation very, very close to C, right? So, here we have a function, sum of cubes, and the value is int n. It is taking one parameter n, which is the highest like n value from 1 to n we have to compute. So, we are just taking input n, and an integer I is there, right? So, integer I is some predefined value is going to be, I mean, I is the value which we are going to take, and we have to compute 1 cube plus 2 cube and so on and so forth. So, 1 to n. So, what basically we are starting with, we are declaring two values, then temporary result equals to, we are starting with the 0 as temporary result. Next step, then we have a for loop, because the value of I from 1 till n, right? So, this loop is going to be executed for value 1 to n, and what we are going to do, temporary result will be assigned the value of temporary result plus I cube. Okay, and the value of temporary result will be returned by this particular statement. So, let's look into the complexity, how we are going to compute the complexity for this particular algorithm. So, if we see line 1, what it is doing, just 2 units of time required, and those are for declaration, which is very, very low time in any case. Line number 2, if we see, then it is simple assignment statement. Okay, so 1 unit of time for assignment. Thereafter, we have at line 3, the for loop has several unit cost. First, initialization. So, we are putting I equals to 1. So, 1 unit cost for initialization. Remember, initialization is going to take place only once. That is why this for loop, initialization is going to be taking place only one, okay, for the entire loop. Cost of testing I is less than equals to n. Now, this is going to happen in every step. Okay, and during the termination, so also, so it will be like this particular step will be executed n plus 1 time, because at the time of termination also it will be checked. So, for the value of n plus 1 also it will be checked, right? Then only the termination is going to take place. So, this is going to require n plus 1 unit cost, and then cost of incrementing, that is I plus plus, which is 1 unit, right? So, this whole loop is going to require these many as far as for loop this particular statement is concerned. Thereafter, this statement, will be executed n times, right? So, now if this statement is to be executed n times, so what would be the cost? This is line 4. So, total cost of the previous for loop happens to be 2n plus 1, but this line 4 is going to be executed for n times, and 2 unit of time, 2 times we are doing multiplication. First we'll multiply I with I, and then this I square will be multiplied with I. So, that's why there are 2 multiplications. 1 unit of addition, this will be added to value temp result, and then next will be one unit of time will be for assignment operation. So, this value will be assigned to the original value of temp result. Therefore, the total cost of this step is 4 times. Why n? Because this particular instruction is going to be executed n times. Okay, and finally, this return statement is going to take just 1 unit of time, and it will be executed only 1. So, if we just add all these values, so what we are getting overall cost to be 6n plus 6. Right. Now, as soon as we go to 6n plus 6, what is this value? CGN, right? CGN plus some constant. So, now C over here, since it is slightly more than that, so we can say C, the value of C is going to be 7. It is always going to be less than 7 like that, and you can find out the value of N0 for that, maybe 6 or something will come out to be that. But overall, if we see that, what is the order of this particular, or big O of this particular order of this particular algorithm is going to be just the linear time, right? Because Gn happens to be n, right? So, this is basically order n only. So, this is the way we can compute the complexity as far as very simple algorithm like I cube, just summation of I cube is concerned. However, they can be slightly more complex algorithms. So how we are going to compute in those cases? So let's first take the case of matrix multiplication. Well, how do we define matrix multiplication? So matrices, first of all, where matrices are needed altogether. Matrices are needed in solving a set of linear equations, coordinate systems, network modeling, etc. So you will find there are many places where networks are used for problem solving domain. Okay, now consider two matrices A and B of the order 3 cross 3 each. So there are two matrices A and B. A is represented, so you know the matrix representation, A11 is the first element, right, the first row and the first column, right. So first represents the row and second represents the column. So this is A11, A12 is the second column, first row, A13 is first row, third column, like that. Okay, second row and the third row. So this is the matrix A, this is the matrix B, and when you multiply these two matrices, okay, what we are assuming that this is equals to C, a matrix C. So our results are going to be stored in matrix C. And how C will be computed? The C is going to be computed. For example, I want to compute C11. So C11, this row, that is the first row. C11 means first row. Okay, so we will pick up all the elements of first row and first column. So first column from B. So I'll multiply A11 with B11, A12 with B12, and A13 with B31. So this is the way we are going to get the value of C, and just sum them up, we get the value of C11. How we do it for C21? So once again, when we are doing for C21, what we have to look for? Row 2. So we pick up A21, A22, A23, and we have to multiply it with column B11, B21, B31. So first column, right? So A31 multiplied by, no sorry, A21 multiplied by B11, A22 multiplied by B21, and A23 multiplied by B31. If we want to represent this information, what we can say, it is Cij. If I want to obtain the value of Cij, it is equals to k. We take another third variable k, and the value of k is moved from 1 to n. N happens to be the dimension of the two matrices, n cross n matrix, and it is aik into bkj. And you can check, suppose k equals to, if I say a11, c11, so what is going to be a11 multiplied by b11 plus A12 k is going from to A12 multiplied by B21, like that. So you will get all these equations. You can get equation for each value of C. So this is the way the matrix multiplication is performed. Now if this is the way, then what is going to be the algorithm for this matrix multiplication? You know the method, right? But then we have to convert this particular method into a simple, very simple algorithm. And this is what the algorithm will look like. So what we have input, two square matrices A and B of n cross n, and output is going to be C, once again n cross n, and matrix what we are doing is multiplying, basically this is a function A, B and C. So C is going to be the output and n cross n is the size, so that is represented by just one variable n. And what is the way the whole thing is going to go on? First, for I equals to 1 to n, and for j is equal to 1 to n. Okay, because we have to compute each and every value, C11, C12 and all that. Therefore, this particular for I equals to 1 to n and for j equals to 1 to n, right? This is what? Cij. So we are doing it for all I and j's. So all ij's are I is equal to 1 to n, for j equals to 1 to n. Cij is for initialized to be 0, and then for value of k to 1 to n, we are just summing up the value of aik into bkj, multiply it, and for this particular loop for k is equal to 1 to n, this is being done. Then it will be done for all the values of Cij in the outside loop. So this is the way the matrix multiplication can be done with the help of an algorithm. But what is going to be the complexity of this algorithm? That is of concern to us. But before we go to that, let's look into an example of execution of this particular algorithm. So for I equals to 1 to n and for j equals to 1 to n, assume I equals to 2 and j equals to 3. So let's take any value 2 and 3. So how it is going? Cij happens to be C2 3 equals to 0. For k is equal to 1 to n, what is going to be? This is going to be C2 3. It was initialized to be 0 outside. So first value, when k equals to 1, it will be 0. When k equals to 2, it will be the summation already summed up value. And what values will be there? Aik. So first, in the first, when the value of k is 1, it is A2 1 multiplied by B1 3. That's what we wanted. Okay. Then in the case when k equals to 2, it is A2 2 multiplied by B2 3. Like that, you will keep on adding these values into C2 3 and you will get the required result. So this is the way we did the matrix multiplication, and this is the way the example. So it is basically proving that our algorithm is quite correct and there is no issue with this particular algorithm. Then what is the analysis of this matrix multiplication? How we are going to analyze it? Now here are 3 loops, right? So the outermost loop will be executed n times, that's all. It's not going to be executed anything more than that. The nested for loop for j will be executed n time for each value of I. So j will actually be executed like this n times. So this will be executed n times. So the overall total number of iterations of these 2 loops, right, are going to be n square. That is, I is equal to 1, j equals to 1, I equals to 1, j equals to 2, I equals to 1, j equals to 3. Let's say n equals to 3. Then I equals to 2. It will move to I equals to 2 and like that, right? Then the j value will once again change from 1 to 3. So thus the loop will be executed, these 2 loops will be executed n square times, whereas j will be executed n times only. Thus, okay, the assignment statement inside the for loop takes constant time as it includes only one assignment. Okay, so after that this is going to take one assignment. The innermost nested loop, now this particular loop, okay, will be executed once again n times for every value of I and j. Thus the loops will be executed, overall these 3 loops are going to be executed n cube times. The statement inside the third loop includes just one multiplication, this is the multiplication, and the one addition and one assignment, right? So these are all, thus will take some constant time. So all these are just one time, right? So these are the constant time for over there. Hence, overall complexity of this whole algorithm is equivalent to the number of times the loop is getting executed, and that number of times loop is getting executed is n cube. So this is of the order n cube. So if you are multiplying 2 matrices of order n cross n, right, the complexity of that algorithm is going to be n cube. Well, these 2 algorithms are fine. Let's try to look into another interesting aspect, which we call exponent evaluation, and how we can use brute force methods to use it. Okay, now the exponent evaluation basically is used in cryptography. In any case, many a times you encounter the term x to the power n. Let's say 4 to the power 10. If you want to compute, how you are going to do that? Well, the brute force method to do so, suppose we want to compute a to the power n, then we are going to express it as a multiplied by a into a, and n minus 1 multiplications are required, just like you have seen in I cube we required I into I into I, just 2 multiplication, right? So n minus 1 multiplication for computing a to the power n. But this is a very, very bad method. This brute force method is a very bad method. And if the value of n is very, very large, then this is not a practical method. Say the value of n is 100, then it is not considered to be a good method, because you have to compute this value 99 times, right? So what can be an alternate method of this? There is an alternate method which is called binary exponentiation, method. Now, binary exponentiation methods are very, very interesting in domain. Why binary exponentiation? Because in binary, the value gets double as you move from the leftmost bit to the next and so on. So every time the value becomes square of the previous value. So let's look into how exactly this binary exponentiation method works. Split the exponent using the binary representation and do the multiplication. So that is the key. So whatever is the exponent. So for example, we have 4 to the power 13, right, where the value of a is 4 and the exponent n is 13. So what 13 in binary is? 1, 1, 8 plus 4, 12 plus 1, 13, right? So 1, 1, 0, 1 is our binary exponent, right? So how you can do exponentiation? So we just put our binary numbers over here, right? So first, that 4 to the power, let's say 1 is 4, right? 1 exponentiation is 4. The value is 1, so this output is 4. Next, we just multiply with this 4 by another 4, right? So what we get? 16. So 4 square, right? So power 2, right? 4 power 2 is 16. However, we have a 0 in the exponentiation, so it's all right. But we still have this 16 as 4 square, right? We know this value. Then in the next step, we multiply 4 square with 4 square, because that is what? The power 2. 4 to the power 4. Now we just square once. Now we are squaring the value of 16. So we square the value of 16 and what we get is 256. The value 1 over here and like that. And over here we get the value 8. So 8, this represents 4 to the power 8. This represents 4 to the power 4. This represents 4 to the power, this is 16 is 4 to the power 2 and this is 4 to the power 1. Right. So when we multiply 4 to the power 8 with 4 to the power 4 and 4 to the power 1, what we get is 4 to the power 13. 8 plus 4 plus 1. The power gets added. When you simply multiply these three terms, you get the required number of computation. Now see how many computations has been reduced from 13, just 1, 2, 3 and 4 over here and 1 over here, 1 extra multiplication. So in total 5 multiplications you are able to compute the 4 to the power 13. Now that is a great saving, and that is how you need to design algorithms. Very simple methods, utilize them and do better as far as computations are concerned. Right. Now if we see then there are two kinds of exponentiations which are going to be possible here. So first is left to right binary exponentiation and another is going to be right to left exponentiation. Well, suppose input A and binary string of length S, right? So binary string is basically representing the exponentiation, okay, and we put it in an array AS, right? So output is final value of A to the power n, and we start with the result as A, and for I from S minus 2, the values, this is what is showing this particular example. So we'll just have you start, this is from top down. So S minus 2 to 0. So you are starting in the array from 2 values after that and then going till 0, because AS means the value are starting from 0, 1, 2, 3 like that, okay, in reverse order. And then you are simply multiplying result with result. That is what, every time you are squaring the value which you have obtained. So, and finally, if what we are saying, if AI equals to 1, then result is basically multiply result with A, and finally you return the result. How this particular algorithm will be executed? So let's compute the value of A to the power 17. So n is 17, that is 10001. S is 5. Result equals to, let's say we are starting with result equals to A. Iteration, we are starting the value of I as S minus 2, that is 3, right? So the value of 1, 2, 3, right? So it is 0. So the result, just we compute A square, A3 equals to 0, so nothing is to be done. Then for value from S, the value S minus 2 was 3. Now we are going to the value of I to 2. and then once again we multiply a square with a square, which is already obtained. We obtain a4, a2 is 0, nothing to be done. Then a4 and a4 is multiplied, a1 is still 0, right? A1 is still 0, and nothing has to be done. And finally, when I equals to 0, the result equals to a8 into a8, and what we are getting over here? Okay, so that is a16, and as per the algorithm, result into a. So we multiply it by a, and we get the value a17. So this is how we are going to compute the right to left. And the complexity of this algorithm. Now, the interesting part of this particular algorithm is that the number of computations are reducing drastically in this particular case, right? So it is going to be just like I showed you, that is going to reduce. If you, the number of computations are going to be 2 s minus 1, s minus 1, and s happens to be n equals to 2 to the power s, so s equals to order of log 2n. That means the complexity of this kind of an algorithm is drastically reduced, and you can compute the results in a much more effective manner, right? So the whole idea is, when you design algorithms, you make sure that the algorithms are able to do something very useful. So what we have done in this session is, it explains the process of analyzing simple algorithm. The three algorithms which we have considered is summation algorithm, whose order, big O order is basically order n, matrix multiplication, which is order n cube, and exponent evaluation, which is order log 2n. With this, we end this particular session. Thanks for being with us.